In this few sections, we're going to look at K in more detail. We're going to see what we can use it for. The value of K can be used to tell us where a reaction is going. If you have a K value that is really, really big, as in much greater than 1, then that tends to mean that the equilibrium lies very far to the right. For example, if I was going to look at this reaction right here and look at the equilibrium expression for this reaction, when equilibrium lies far to the right, that means I'm making a whole lot of y, so y is really large, x will be really small, that'll give me a large value for k. The exact opposite happens if you have a really small value for k. That means you have a lot of x and very little of y. That means equilibrium is going to lie far to the left. In general, whenever equilibrium lies far to the right, you end up with a potential energy diagram that looks something like this. This is another one of our exothermic diagrams where you have a negative delta H or delta E. It doesn't have to look like this, but most of the time this is the type of potential energy diagram you're going to see here when you have a lot of products that are being made. One thing to keep in mind is that time is not really related to equilibrium whatsoever. A lot of students will think that since it has a large value for K, makes a whole lot of products, that means that it is going to happen really fast, but that is not true at all. All it means is that it makes a bunch of products, but it may happen quickly or it may take it a really long time to happen. So rate has absolutely nothing to do with the value for K at all. Other things that we can do with equilibrium constants is we can manipulate equilibrium and equilibrium equations to find other equilibrium constants. This is going to be very similar to Hess's law with a few key differences. For example, the first one we've already seen. The equilibrium constant of an equation in the reverse direction is going to be the inverse of an equilibrium constant in the forward direction. Now remember, in Hess's law, if you flipped a reaction, you made the value of delta H negative. In equilibrium constants, if you flip a reaction, then you take the inverse of K. Look at letter B here. The equilibrium constant of a reaction that has been multiplied by a number is equal to is being raised to a power that equal to that number. Remember, in Hess's law, if you multiplied an equation by a coefficient, if you doubled everything in the equation, then it would double the value for delta H. In this case, it would square the value for K, or if you multiplied everything times 3, it would cube the value for K. So we're raising it to a power this time. And then lastly, if you add together equations to get an overall equation, remember in Hess's law, you would add together the value for K's, but with equilibrium constant, you are going to multiply together the value for K's. You're going to find the product. So let's take a look at an example of this. We have two equations and an overall equation. And it wants us to find the value of K for our overall reaction here, for the one that's in red. So I'm going to take a look at, this is just like Hess's law, I'm going to take a look at the substances and figure out what to do. So if I look at this first reaction here, I notice that I have one HF here, two HFs down here in my target equation, so that means I'm going to try to multiply everything by 2. And remember what we just saw, that if you multiply the equation by 2, you're going to raise your value to K to a power of 2. So you're going to square your value for K. If I take a look at my second reaction here, I notice that my H2C2O4 is on the wrong side. So I'm going to have to flip this equation. And when I flip this equation, remember that I'm going to take the inverse of the value for K. So if I take these two equations and add them together, I should get the target equation. Let's see that. Okay, so here's the two equations added together. If I take out the 2H plus, which will cancel out, I am left with my target equation, so that's good. And so since I can add these two equations together to get my target equation, that means I can multiply, get the product of my two K values to get my overall value for K. And when I do this, I get a K value of about 0.12. In this section, don't forget that the only substances that should be included in your equilibrium expression are either solutions or gases, that you should not include pure solids or pure liquids in your equilibrium expression. It's a very common mistake to include them in problems when they ask you to write an equilibrium expression, so watch out for that. And then let's see how we're going to calculate equilibrium expressions. This is a really important section that we need to make sure that we know how to do. There's certain steps that we're going to use to calculate our equilibrium expression. The first thing that you're going to do is you're going to make sure that you have a balanced chemical equation. Usually they'll give you one. If they don't, you need to write it. Secondly, you need to write your equilibrium expression. Usually, this is the very first thing that they're asking you to do in the problem, is write the equilibrium expression for the reaction. The next thing we're doing is we're setting up an ICE table. ICE is an acronym that stands for Initial, Change, and Equilibrium. Then the next thing we might have to do is we might have to calculate something called Q, the reaction quotient. We'll get into that later. Next, after we've set up our ICE table, is we need to figure out what sort of change we're needing to reach equilibrium, depending on the equilibrium values that they have given us. Then we're going to figure out what our equilibrium concentrations are. Then we will plug our equilibrium concentrations into our equilibrium expression that we got back in step number 2, and we will solve for K. It is really important that you only use the equilibrium expressions for your problem. Don't use the initial or the change. So let's go through an example of this and see how this is done. It goes ahead and it gives us the balanced chemical equation. That's good. So the next thing I'm going to do is I'm going to write my equilibrium expression. Alright, so here's my equilibrium expression. I can include all three in my equilibrium expression because all three are gases. And now I'm going to set up an ICE table. I'm going to make this a little bigger, otherwise I won't be able to fit everything on here. Alright, an ICE table is ICE. I is initial, C is change, E is equilibrium. If I look back at my problem, it tells me the initial concentrations of the H2 and I2, so I'm going to go ahead and plug those in. And initially we don't have any HI in the container at all, and that's going to be true for a lot of these. And then it tells us it's allowed to reach equilibrium, and it says that the concentration of the HI at equilibrium is 1.8 times 10 to the negative third. So that's going to be the value for E for my HI. Now what I've got to do to be able to plug my numbers back into that thing there is I need some equilibrium values for H2 and I2 as well. So what I can use is I can use this to figure out the change that happened with the HI, and thus the change that happened in I2H2. So let's see how that works. If I went from 0 to 1.87 times 10 to the negative third, that means that my change must have also been 1.87 times 10 to the negative third. Now, according to this mole ratio here, for every 2 moles of this, I've got 1 mole of this and 1 mole of this being used up. So I am using up half the amount of I2 and H2 that I am making of HI. And so half of 1.87 times 10 to the negative third, which is 0.935 times 10 to the negative third, is how much of these two I'm going to be using up. So I know how much I started with, I know how much I'm using up, I subtract those two, and I can get my equilibrium values. Now that I have my equilibrium values, I can plug these in to my equilibrium expression that I got earlier. And then I can go ahead and solve for my value of Kc, and I get around 51. Last thing that it says in your notes is if you have really, really small equilibrium constants, then you can assume insignificant changes, and it makes the math a lot easier. Now, I'm going to go through some examples of that with you in class and show you how that works.